Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on module the infrared astronomy. Generally we abbreviate as IR-Astronomy under the paper of Astronomy and Astrophysics. After completing this module, the students will be able to learn how infrared radiations, which are of course the part of electromagnetic spectrum, were first discovered by William Herschel. To learn the quantity optical throughout OT of the telescope and for a detector and its specific relevance and use in the infrared astronomy, knowing the transmittivity at a certain wavelength of infrared radiation with a given value of the layer denoted L of the perceptible water, we can obtain the transparency for other values of L of the infrared radiations. To start with, the basic studies the definition of the infrared astronomy. The infrared astronomy began in 1830s, a few decades after the discovery of infrared light. The infrared light is the electromagnetic radiation with wavelength ranging from 0.75 to 300 micrometers. The infrared part of the electromagnetic spectrum comes after the visible light shown in the figure. The discovery that some celestial objects emit most of their radiation in the infrared region of the spectrum has stimulated an increasing growth of interest in the field of infrared astronomy. But important thing is that this progress was very limited. It was not until the early 20th century that conclusive detections of astronomical objects other than the sun and moon were detected in infrared light. After a number of discoveries were made in the 1950s and in 1960s in radio astronomy, astronomers realized that the information available outside of the visible wavelength range and modern infrared astronomy was established. The airborne, balloon and rocket experiments have been performed to observe these sources outside the atmosphere or at a high altitude. Now, why this infrared astronomy seems to be very important? The reason is that the infrared light is absorbed at many wavelengths by water vapors present in the Earth's atmosphere. As we have already said that there is an atmosphere which belongs to our Earth. The radiations means the light coming from different sources have to come across, have to pass through this atmosphere. Of course, few very high energetic radiations like gamma rays, X-rays, even for that matter the ultraviolet radiation is being prevented by the Earth's atmosphere. So, this Earth's atmosphere has a role in every kind of observation, whether it is a UV or whether it is IR. As we have said here that the infrared light is absorbed at many wavelengths because of the presence of many water molecules. So, most of the infrared telescopes are at high elevations at dry places, above as much as of the atmosphere is possible. In fact, this is related to selecting an appropriate site for having an observational facility anywhere. So there are very specific reasons that why the IR telescope is to be installed at higher elevations, at dry places, above as much as above the atmosphere as possible. There are also infrared observatories in space. For example, including the Spitzer Space Telescope and the Herschel Space Observatory. These observatories we refer here because they have already revealed, they have already given some very important results. So the extensive ground-based observations have also been carried out through the atmospheric windows in the near infrared, intermediate and very infrared, and in spite of atmospheric windows, the constraints introduced by the presence of a residual, non-negligible atmospherical emission, infrared astronomy from ground observatories appears to be a valuable research tool. There is a specific reason for this. This is because of the flexibility of ground-based observations exceeds that of high altitude observations. Now the realistic situation to be discussed about the best ground-based infrared telescope depends upon several parameters and on several features such as the operating wavelength range, the matching problem between the detector and the telescope, the atmospheric contribution, and the main aim of the observer, that is, mapping the sky or study of some well localized faint sources or solar astronomy. So, let's talk here about the basic history of the IR astronomy. The infrared astronomy, or we can generally call it as the infrared radiation, was actually discovered by William Herschel, who performed an experiment where he placed a thermometer in sunlight of different colors after it passed through a prism. He noticed that the temperature increase induced by sunlight was highest outside the visible spectrum, just beyond the red color, that is, the temperature increase was highest at infrared wavelengths due to the spectral index of the prism rather than the properties of the sun. The fact that there was any temperature increase at all prompted Mr. Herschel to deduce that there was invisible radiation from the sun. He went on to show that such radiation could be reflected, could be transmitted, and could be absorbed just like a visible light. Since such radiation has wavelength larger than visible light, so it was not known as infrared radiation. Then the efforts were made starting in 1830s and continuing throughout the 19th century to detect the infrared radiation from other astronomical sources. The infrared radiation from the moon was first detected in 1873 by William Parson. So the field of infrared astronomy continued to develop slowly in the early 20th century as Seth Barnes, Nicholson, and Edison Pettit developed thermopile detectors which are capable of accurate infrared photometry and sensitive to a few hundreds of stars. The field of infrared astronomy was mostly neglected until 1960s, with most scientists who practiced infrared astronomy having actually been trained physicists. The success of radio astronomy during the 1950s and 1960s, combined with the improvement of infrared detector technology, it prompted more astronomers to take notice, and infrared astronomy became well established as a subfield of astronomy. When we talk about the infrared astronomy, the most common infrared detector array used at research telescopes are HGCDT arrays, which operates well in between 0.6 and 5 micrometer wavelengths. For longer wavelength observations or higher sensitivity, other detectors may be used, including other narrow gap semiconductor detectors, low temperature bolometer arrays. The special requirements for infrared astronomy include very low dark currents to allow long integration times, associated low noise readout circuits, and sometimes very high pixel counts. Low temperature is often achieved by a coolant which can run out. Space missions have either ended or shifted to warm observations when the coolant supply used up. For example, WISE ran out of coolant in October 2010, about 10 months after its launch. So, it's also important to see that how there can be a matching between the telescope and the detector. A telescope is said to be optically matched or in optical contact with a detector if a simple kind of a mathematical equation is obeyed, like AD phi d is equivalent to AT phi t, where AD denotes the detector area, phi d is the solid angle of field of view of the detector, and AT phi t have the same meaning for the telescope. So D denotes the detector and T denotes the telescope. The quantities AD phi d and AT phi t are frequently known as optical throughout, denoted by OT of the detector and the telescope respectively. If the optical throughout of the telescope is large than the optical throughout of the detector, then the latter is excited by a fraction of the energy collected by the telescope, while in opposite case other rays in addition to those coming from the telescope reach the detector. In both the cases, the degradation is expected in the system performance, so that the condition that we discussed, like AD phi d is equivalent to AT phi t, is that of an ideally operating telescope detector system. Moreover, as the optical throughout of the telescope increases, we may observe more sources in the shortest possible time. More precisely, by increasing AT, fainter sources can be detected, while with increasing phi t, the time required to perform a survey of the sky decreases. So, in principle, the optical throughout must be kept as large as can be made possible. So, for IR astronomy, how we take care of the sites for observations? Sites for observations. The most important contribution to the atmospheric observation is due to the presence of water and the carbon dioxide in the near and the intermediate IR region, and to water molecules in the far infrared region. As already said, that atmosphere plays an important role in having the IR observations. Therefore, the presence of water molecules and the carbon dioxide molecules in the given part of the atmosphere makes it clearly distinct to see that which one site shall be preferred for having an observational facility. So, if we assume that the absorption coefficient at a given wavelength is, say, S for water, and as the content of water in the atmosphere increases, the absorption also increases. We introduce a layer L of the perceptible water so that the absorption will depend upon both S as well as on L, or we can say that it depends upon SL. However, the Lambert law of the exponential absorption is no longer valid for bands made up of discrete lines, and the effect of the layer on the transmittivity as shown in the given figure. If we know that the transmittivity at a certain wavelength with a given value of L, we normalize the given curve shown in the figure at the same value of L, and then we can talk about the transparency for other values of L. Some people have already worked on the rough estimates of this L. Practically, L ranges from 10 millimeter at sea level with a high humidity site to a level to a range 0.7 millimeters at a high altitude over 3000 meters. While seeing the graph in the given figure, by having a change in L. So once we change the scale L, we see how the ratio with a given percentage shown in the vertical direction changes, and then suddenly there is a dip, and finally it ultimately reaches to the horizontal line. So this kind of an observation, based on various theoretical and some mathematical studies, can be used as a tool to see if we, for example, we are selecting at 10 sites and we have to do some IR observations. For that, we have to install an IR telescope. So, out of 10 sites, we can select one of the site whose appropriate results corresponding to S and L will be like same that we have discussed here. In the world scenario, there are some important sites. Certain sites are very important. Perhaps they are important because they have the unique features. In the earlier of my discussion, we talked about the places where IR telescopes can be installed. There are sites. As we said that we should go above the sea level and more higher. And also, such sites should be free from any kind of this disturbances. It's not only that the scientific things have to be important for selecting a site in reference to the IR telescope, but there are some social effects, like the site should be always less affected by the public, less affected by the transport. Those are, of course, the social things, but we have to keep more scientific things into consideration that we have discussed while selecting the scale for S and L, and also see that in our telescope how there can be a matching between the telescope and the detector by following a very simple and an important kind of a relation decided on the basis of AD phi D to be approximated by AT phi T. So students, let us see what we are going to learn in this module. The discovery of astronomical objects other than the sun and moon, emitting the infrared radiations, made the realization that the information available outside of the visible wavelength range, and so the infrared astronomy was established. In optical infrared astronomy, the quantity which we have referred to as OT, the optical throughput of the telescope, must be kept maximum and is defined as the product of the area of the telescope and solid angle of the field of view FOV of the telescope. The transmittivity of infrared observation through the atmosphere containing water molecules. Thank you.